spend at least some of this time talking about the half reaction method. So this is the alternative method that can be used for balancing oxidation reactions. Now, like I said, this does have some utility in terms of electrochemistry. If you have to take Chem 2, you will see electrochem in that course. Redox reactions will be part of that because redox reactions run electrochemical reactions. And this is the way that they are presented in terms of these half reactions. But in terms of the balancing of equations using this method, what you'll find is that it is considerably a longer process. And so if you look at the process itself, there are 5 primary steps. Now, I say that a little bit tongue-in-cheek because step 3 here has many sub-steps within it to balance each half reaction in total and in turn. But it can be done. And so the process starts the same way. We start with oxidation numbers. We then use those oxidation number changes to split the reaction into half reactions, an oxidation half reaction and a reduction half reaction. And then our next step is to balance those half reactions, multiply the half reactions to make sure that the number of electrons coming in and the number of electrons going out are the same, and then do any kind of cancellation that is necessary. And so let's kind of get into the process a little bit here, and I'll kind of show it off. So for balancing, there are actually different procedures for balancing in acid versus balancing in base. So what I'll do is I'll show you the directions for how to balance it in acid, and then I'll show you how we tweak those directions just slightly to balance it in base. And so for balancing an acid, what we do is we first start by balancing everything that's not hydrogen or oxygen. Then we balance the oxygens using water. We balance the hydrogens using hydrogen ions, H+, and we balance the charge using electrons. And so we would do this for each of the half reactions. And then we'd go back here, and once we had our half reactions, we would multiply them to make sure that the electrons that are being left out by the oxidation are being taken in by the reduction. And then we add them together and cancel anything that's common on both sides. Now, if we are in base, it's very, very similar. The only difference is that at the very end, and I'm talking the very end, this step 5 end, at the very end, we simply convert the hydrogen ions and hydroxide ions and interchange them with each other. And how we do that is we add equivalent amounts of hydroxide to each side. And so that's how we get it to remain balanced. The hydrogen ion combines with the hydroxide ion to make water. The hydroxide ion on the opposite side stays hydroxide ion, and we'll have extra water molecules left over, and we'll just end up canceling them out. So this says that we're going to balance it in acid only. We're going to balance it in both using the half reaction method just to show it off. So our first step in this method is the same as the first step it was in the previous method as well, assigning oxidation numbers. So oxidation number for manganese here is +2. The oxidation number for the bismuth here is +5. And for the oxygen, it's -2. For the permanganate, manganese is 7. And oxygen is -2. And in the bismuth, it's a positive 3. So this is our process. We've got everything set up. Now we just need to break it up into half reactions. So for our oxidation half reaction, we can see that the manganese is going from positive 2 to positive 7. So that's going to be the reaction that we are starting with. Manganese plus 2 turns into permanganate MnO4 minus 1. And our reduction half reaction, leave a little space, our reduction half reaction is going to involve the bismuthate ion, BiO3 minus, turning into bismuth 3 plus. So this is the reaction that's going on in both circumstances. Now our first step would be to balance everything that is not hydrogen or oxygen. And in this case, it's pretty easy. I have one manganese on this side, I have one manganese on that side, so that one's balanced. I've got one bismuth on this side, I've got one bismuth on that side, it's balanced as well. So that part's taken care of. Second step, I need to balance oxygen by adding water to the opposite sides. So I have 4 oxygens here. That would require 4 water molecules on this side. I have 3 oxygens here. That would require 3 water molecules on this side. The next step would be to balance hydrogens using hydrogen ion, H+. So I have added 8 hydrogens in total to the reactant side in the oxidation reaction. I'm going to need to add 8 hydrogen ions on the product side to counterbalance it. I've added 6 hydrogens in the form of water here. I'm going to need to add 6 hydrogen ions to the reactant side to balance it out. And then my last step is to balance electrons, to balance charge using electrons. So very similar to the process that we did before. I need to draw a line down the middle.
Mr. Brown.
Yes, Chastity.
Okay, it's a quick question. If it was hydrogen, if it was an equation with hydrogen, you would just need to add the oxygens? If it wanted it acid only?
So if it wants it in acid only, your first step is still to balance the oxygens. And if there were hydrogens on this side already, I would just take that off. So let's say that there was already, there's already 2 hydrogens over here on the reactant, right, or on the product side. I would only add 6 hydrogens instead of 8.
Okay. Go ahead. Okay, I'll process it.
Okay, so we're to the part where we're evaluating charge. Excuse me. On the reactant side, I've got a positive 2 charge from the manganese, and I've got 0 charge from the waters. So total charge on the reactant side is positive 2. On the product side, I've got a negative 1 from the permanganate and 8 positive ones from the hydrogen ions. Total charge over here is +7. And so I would need to add 5 electrons to this side to get rid of that extra positive charge. And so the electrons always go on the side that is too positive. That has extra positive charge. And so now I've got those charges to even out. I can rewrite my half reaction. My half reaction is going to be manganese 2 positive plus 4 waters makes permanganate ion plus 8 hydrogen ions plus 5 electrons. And so this is my oxidation half reaction. For the reduction half reaction, we've handled everything so far other than the charge. Total charge, I have a -1 from the bismuthate ion and 6 positive ones from the hydrogen ions. Total charge over here is +5. And on the other side here, I have a +3 for the bismuth and 3 uncharged water molecules for a +3 over here. To balance the charge, I need electrons. So I'm going to have to add 2 electrons to this side. And the 2 electrons are going to take that +5 to a +3 so that the +3s now match up. In a similar fashion, I've got everything balanced up. Let's go ahead and write the half reaction. It's BiO3 -1 plus 6 hydrogen positive ions and 2 electrons, making Bi +3, bismuth 3 ion, and 3 waters. Okay, and so with these 2 half reactions, this is, we've only gone part of the way. We are now through step 3 of our 5-point procedure that we talked about. The next step is we have to evaluate the number of electrons that are leaving the manganese versus the number of electrons that are coming into the bismuth. And we can see that the 2 are not equal. 5 are being deposited by the manganese, 2 are being turned into the bismuth, and so we need to equal it out so that just as many are leaving as are coming in. And just like we did in the previous method, the way to do that is through a lowest common multiple. The lowest common multiple between 5 and 2 is 10. So I'm going to multiply both equations by a number to get them to 10 electrons either gained or lost. And that means that I'm going to have to take the manganese half reaction, multiply it by 2, and the bismuth half reaction and multiply it by 5. And so what this will look like afterward, 2 manganese positive 2 plus 8 water makes 2 permanganate ions, 16 hydrogen ions, and 10 electrons. And if we add that to our other half reaction, 5 bismuthate ions and 30 hydrogen ions and 10 electrons make 5 bismuth 3 plus ions and 15 waters. Those are our 2 half reactions. Now we can see that I have equal amounts of electrons on each side. Since I have that, I can now combine them together, and I'm actually going to have to put the result down a little bit lower here because it's going to take up a lot of space. So the net result, which we'll put here in black, is 2 manganese positive 2s, 8 waters, 5 bismuth 8 ions, 30 hydrogen ions, 10 electrons, 2 permanganate ions, 16 hydrogen ions, 10 electrons, 5 bismuth 3 plus ions, and 15 waters. This is the balanced equation that we would run into. Now, there is some extraneous, there's some fluff here. There are things that are common on both sides that would be in our best interest to get rid of. In particular, we can look and see that I have water common on both sides, I have hydrogen ion common on both sides, and I have electrons common on both sides. So similar to what we saw in net ionic equations yesterday, we are going to want to cut some of the things that are common because they cancel out. So the 10 electrons can cancel out. Let's see, I have 8 waters on the reactant side that can negate 8 of those 15 waters on the product side. So that 8 becomes a 7. And I've got 16 hydrogen ions on the product side that can negate 16 of those hydrogen ions on the reactant side. And so if I do one more rewrite here, the final equation in acid is 2 manganese ions, 2 manganese 2 plus 5 bismuthate ions, plus 14 hydrogen ions make 2 permanganate ions, 5 bismuth 3 plus ions, and 7 waters. That is the final, at last, equation for this reaction in acid. So, like I said, individually, oxidation half reactions, reduction half reactions aren't too terribly difficult to do. And even in the combining out process, this isn't terribly difficult. There is a reason why this method is preferred by some students and by some faculty members for that matter. The bottom line is the hard part is really there's a lot of process. There's a lot of steps in here. It took us 20 minutes to do this problem. Whereas in the same light, we did in 20 minutes acid, base, and part of a third reaction using the other method. So there is some utility to this. Don't get me wrong. I'm not going to completely bash this technique, but it is a good bit deal longer. And there are lots more steps to do, lots more mistakes that can be made along the way. And we haven't even done the base part. For the base part, if we take this equation up here, to convert it into base, what I need to do is there is no H plus, or at least very little H plus, available in base. So what we do to more or less combat that is we're going to add equal amounts of hydroxide to each side of the equation. When we do that, it's going to turn the hydrogen ions into waters. And the second thing it's going to do is it's going to create another situation where we have to cancel because I'm going to have waters on each side. So these 7 waters negate 7 of those waters. And so the net result for base would be 2 manganese 2 pluses, 5 BiO3 minus bismuthate ions, 7 waters, making 2 permanganate ions, 5 bismuth 3 ions, and 14 hydroxide ions. And so once you get it in acid, turning it into base isn't usually that difficult. Sometimes, if we find that our hydrogen and our water are on opposite ends, literally all that happens is that it flips around. The waters move over to the reactant side, the hydroxides move an equal and opposite number to the product side, or vice versa. Where it gets a little bit complicated and tricky, there are some occasions because of hydrogen content in some of the reacting species where water and acid end up on the same side of the equation. And then that's the case where you can't do that. And you have to actually go through and do the math. But if hydrogen and water are on opposite sides of the reaction, then literally all they do is switch places. And the H plus becomes OH minus. And that's how you fix it for a base as opposed to an acid.